Ladies and gentlemen, in this video we will focus on one of the main three pillars of tailored light, the spectral quality, which is the color of the light. So in physics terms, the frequency, the wavelengths. How do we generate different wavelengths in a laser? The content is definition and motivation, theoretical background, three-wave mixing, phase matching, and in the end, concepts of nonlinear conversion. The definition of frequency conversion is displayed here. We start with an initial frequency omega-1, and then we end up, after we go through the magic box, with a different frequency omega-2, and the difference between those two energies of course compensates the individual frequencies for the conservation of the energy. Why do we need several colors, several wavelengths, several frequencies in lasers? Here are some application perspectives, for instance in projection or display, where we need the three main colors, RGB, or in laser beam processing, when we want to weld copper, for instance, we take radiation which is highly absorbed by copper, which is in this case green radiation. Or think simply of the processing of glass. You wouldn't do that with a visible light laser, but with an infrared laser, which is absorbed in only a few nanometers in glass usually. A more future-oriented perspective is the direct resonance of wavelengths with resonances of the individual molecules. So for biophotonic applications in which we want to stimulate very specific atomic or molecular vibrational modes, we have to have laser sources with the corresponding very narrow line widths, coherent properties. If we talk about scattering, Raman scattering, coherent Raman scattering for analysis, for instance, then we want to have very specific wavelengths for the resonance in these molecules. To sum that up, so basically we need the wavelengths for the increase in process efficiency or to access very new fields of applications in photonics. The technical realization of frequency conversion is displayed here. We, in the simplest case, have a frequency doubling. In this case, a YAG laser is doubled to a green laser in 530 nanometer wavelengths. Here, harmonic generation, we use extreme nonlinear scattering effects at atoms, at electrons, at atoms. So with extreme intensities, laser intensities, we can generate up to the 17th, the 20th harmonic of a initial wavelength. In this case, a 1 micronanometer radiation has been converted to 60 nanometers in the 17th harmonic. Or in a continuous mode of operation, we can use tunable systems. We need wide broad frequency bands in amplification in the active media, for instance in a dye or in a titanium sapphire laser with very broad frequency band of amplification, and then we can tune the laser in this frequency band continuously, so to say we have a knob for frequency at this laser. Now let's talk about technical realization, and to reduce the complexity we focus here on frequency doubling, as you see here in this example, where we come in with an infrared laser and in the magic box something happens which turns it into a green laser. Exactly half the wavelengths, double the frequency. In this sketch here, you have to imagine E1 equals E2, so we come in with similar photons and end up with the frequency doubling. What happens in this magic box? Imagine you apply an electric field to some atomic system. What we get is a polarization, so the electric field polarizes the matter, and the polarization direction, of course, depends on the direction of the electric field. If we turn this around, of course the polarization will again change by 180 degrees, and we will have the polarization in the exact opposite direction. Now usually these effects are considered to be linear, so the displacement with relation to the force is usually considered a linear relation, so we have a linear combination of the electric field and the polarization. At higher intensities and in a more detailed view, of course, we not only have a dependency on the first order of the electric field, but on the square, on the third power and the fourth, and so on. So this describes the domain of nonlinear optics, whereas if we only take into account a linear relation between electric field and polarization, we are in the domain of linear optics. The wave equation, using also the nonlinear parts, then will be modified, and corresponding, if we take a look at the harmonic behavior of the matter, of course it becomes non-harmonic. Here you see in the dotted version the harmonic potential, as you all know it, from a linear connection of the exciting force. Then the reaction of a linear system will be linear, and we will have this parabolic energy spectrum. However, if it becomes nonlinear, if you have higher order terms, then this relation becomes nonlinear. And you immediately see that we don't have single resonances like in the harmonic oscillator, but now we have a, depending on the expansion, a totally different behavior with different spacing of energy levels, so a nonlinearity in the system. And that allows us the multiplication or the change of the frequency. Again, in a more general notation, if we take into account not only the linear dependence, but the first nonlinear term, which then is proportional to the square of the electric field, in a more general level again, now we talk about three-wave mixing. Again, of course, E1 and E2 are equal for frequency doubling because it is just one source. But we talk about three-wave mixing because we have one wave, a second wave. In this example, they are the same. More general, they are not the same. And they result in a third wave. So we talk about three-wave mixing. So what can happen if we mix three waves in three-wave mixing? Well, we can have simply second harmonic generation, frequency doubling. We can have difference frequency generation, sum frequency generation, and optical rectification. And that is simply accessible by looking at the solution if we superimpose two electromagnetic waves and look at the resulting polarization. The nonlinear part will show this combination of terms, and if you multiply those out, then you get solutions either 2 omega 1 or 2 omega 2, which is second harmonic generation, the difference frequency, the sum frequency, or the differences of the two frequencies, which is referred to as optical rectification. Now, a very important issue is the phase matching. If we look at the effect of superimposing the initial waves, now think again of frequency second harmonic generation. So we have two photons of this wavelength which generate one photon of this wavelength. This is indicated along the lines of the nonlinear crystal, the length of the crystal. So the pump source will decline in intensity or in electric field, and the resulting frequency, the signal, will increase in electrical field strength over the length of the crystal. This will work best if the two waves are exactly in phase, so that the intensities locally really add up and we can make the conversion with a high efficiency. As a consequence, if we look at this ideal situation, the difference in wave vectors should be 0 in a limit. If we have a phase matching condition that these differences in wave numbers are 0, then we have no change of the relative phase of these stimulating and frequency doubled signals, but in reality this is not always the case. Well, the momentum conservation just gives us that the difference of K3 to K2 to K1 is a certain value, and this at the best of course is 0, and then we have the maximum transfer of the energy. In actual reality, however, unfortunately, the indices of refraction are not equal at the pumping wavelengths and the resulting frequency doubled signal. In other words, if you look at a real material, a real glass in this case, BK7, there's a significant change of the index of refraction with the wavelength. So if we change from 1 micron to 500 nanometers, you immediately see the difference. And so the material will treat those two waves differently. So there's generally no phase matching in isotropic materials that have a normal dispersion. And as a consequence, we need to come around this by a trick. And one of the most used and most elegant tricks is that we use bifringent crystals. We do have crystals which behave depending on the axis of orientation, which behave with different indices of refraction. An alternative I will go to later on also would be periodically poled crystals, which we will come to later. Now, the first thing, bifringent crystals. Here you see the index of refraction of a bifringent material, in this case for the wavelengths of 532, the green light, so the frequency double signal, this is this one here, with a dependence on the angle in this bifringent crystal. And this here is the index of refraction of this bifringent crystal for the pump wavelengths. Now, of course, these two curves have intersection points, and if we choose an orientation of the angle exactly such that we meet this intersection point, then the index of refraction of that crystal for the green light will be exactly the same as for the pumping light, which means, as a consequence, we have no difference in index of refraction for the two wavelengths, and thus delta K equals 0, which is phase matching. So phase matching is achievable in many cases if we use a suitable choice of polarization, propagation direction, and temperature. Temperature also can influence this behavior. In a even more detailed view, you see here now the propagation in this bifringent crystal, and the pump signal will just go through that crystal straight, but for the fact that we have a different group velocity of the green, the resulting laser, the signal, then of course if we have the same phase, we need to have a different path of that beam. So there will be a systematic walk-off, as we call it. So the green light will be deflected under a certain angle depending on the difference in index of reflection. So we will have a spatial displacement of the beams through their propagation through the crystal. How can we handle that? Again, if we look at the conversion efficiency, this is maximum at no phase difference, no phase change. So at delta K times the length of the crystal equals 0, we have the maximum efficiency. So that's the point we want. As soon as we get away from this and we have no phase match, then we will have losses in conversion efficiency. Let's take a look at it in more detail. This is the crystal length, and on the ordinate we have the conversion efficiency. Of course, the conversion efficiency is maximum, and we get maximum conversion for delta K equals 0. As soon as we have non-zero phase change, we will have, depending on the size, we will have rather quickly a change of the reaction in the crystal. So a positive phase change will change to a declining phase change and so on. It will be a periodic behavior. Ultimately, we will have back conversion from the frequency doubled curve to the original pumping wave, depending on the phase change. So again, in the best case, we have no problem. We have along the crystal a maximum conversion with 0 phase change. However, in reality, we have to live with phase change. So what can we do? What we can do is so-called poled crystals. We can take periodic poled crystals. Again, let me go back. You see already what happens. If we would be able, at this point, for instance, in the blue curve, so to say, to change the sign of what happens thereafter, then this curve would go on like this. And again, at this point, we would change the sign, and again, we would have an increase, and so on. So we stop the crystal at this point and take a, so to say, inverse crystal, inverse poled crystal. Here you see an example. Here you see the pole characteristic indicated by these green atoms in a complex crystal structure. If we just, so to say, take the inverse of that and place it in the other side or turn around the crystal, then we have the effect exactly in the other direction, which ultimately leads to a periodically poled crystal, which then allows us, as a result, depending on the phase change, of course, if it is phase matched, we will have no difference, we will have the maximum efficiency. But then if we use the poled crystals, we can, so to say, stack the right conversion to the next level by changing the polarity of the crystal, and thus again still have an increasing efficiency and conversion throughout this crystal. Now finally, in reality, the world looks a little more complex, and the index of refraction is not only depending on the wavelengths, but it depends also on the temperature and on other issues. So we have fluctuations of temperature in this crystal, which makes life difficult. Of course, we discussed the wavelengths dependency. And we have angular deviations through misalignments. So again, also this angular matching condition in reality needs to be addressed professionally. And so usually we have to live with the fact that phase matching is not possible to the full. Some concepts on nonlinear conversion. In the first case, it's very easy. We have a laser. We have a focusing lens in order to get enough intensity for the nonlinear effects to be stimulated in this nonlinear crystal, and we get an extra cavity conversion to the, in this case, green light. We also could use this crystal intracavity. So we use a dichroitic outcoupling mirror. We have a pumping cavity, the nonlinear crystal, and we take out only the converted light, which immediately indicates from intuition that we will have a higher conversion efficiency. And last not least, we can have the conversion within the laser resonator directly. So we have a laser crystal and actively now in the actual laser cavity include also the conversion to the, in this case, green laser light. So this actually concludes the session. I just want to give you one example of a frequency converted laser, which you may have had in your hands already. This is a green laser pointer as it is commercially available. And let's take a look inside. How is this green light generated? And you see most of the device content is the power supply, the batteries. And here's all of the laser activity. This is enlarged here. So we have the pumping diode, which pumps a solid state laser crystal, which is located here. Directly attached to it, the frequency converting KTP crystal. That's where the 1 micron radiation is generated. Directly attached to it is the frequency converting crystal, the KTP crystal. And the resonator has to be imagined between here and here. So we have an intracavity frequency conversion system, which then is expanded, collimated to give us the laser pointer beam. So, as a consequence, we now know how to convert frequencies in nonlinear media. Basically, we focused on frequency doubling, but with the three-wave mixing concept, you are aware that you can generate any type of sum frequency, difference frequency, ultimately resulting in the full spectrum of light and laser radiation in frequency. So we are able to cover a huge range of frequencies from the ultraviolet all the way until into the far infrared, 10 microns, 20 microns, depending on the nonlinear crystals that we use for the conversion.